Hello, engineers. Welcome back. How are you all? I hope everybody is doing okay. I know it's been a while since my last video. I do apologize. I just had to take care of some stuff, but all that is done now, and we can surely get back on track. So, without any further delay, let's get started. So, in the previous video, we saw just a quick recap about binary trees. So, a binary tree is a tree with maximum two children per node. A root node can have a left node and a right node, and the left node can have its own left node and a right node. And we were inserting the elements from left to right. So, if there was a new element, first we would go uh, one level at a time and we would fill from left to right, right? So we saw all this in code, we saw all these operations, and we discussed also the time complexities. So in this video, we're going to look at a new tree, which is called a binary search tree. So this is a variant of a binary tree. So let's see how this tree looks like and what are the operations that we can do with it and what is the structure of it, right? So let's get started. So what are binary search trees? So like the word says, it is a binary tree because it is still a tree with two nodes. So let's say I have a tree like this 50 and then I have 60 and 70. So there are two children per node. So a maximum of two children per node. So that property is still valid, right? So first is it is a binary tree, which means maximum of two children per node. And secondly, it is a sorted tree, which means that every element that is to the left of a node should be less than this node, and every element that is to the right of the node should be greater than this one. So this tree that I have drawn 50, 60, 70 is not a valid binary search tree. It would be valid if this element is less than 50. For example, instead of 60, if I had 40, then this is a valid binary search tree, which is also called as BST in short. So for every node, the left element should be less than the parent node and the right element should be greater than the parent. So let's take another example. Let's say we have a root of 100. So whatever is in the left tree should be less than 100. For example, let's say there is 90 here and there is 110 here. So far, the structure is valid. And whoever are the children of 90 should again follow the same structure. For example, there can only be 80 and 95 here, let's say. So this is still valid because 95 is still less than 100 and 95 is greater than 90. So the right children should be greater than the parent and the left children should be less than the parent. So if we look at this whole left tree from 100's point of view, every element is less than 100, right? Similarly, if we take the whole right subtree, every element should be greater than 110. In this, if the tree is satisfying this property, then it is called a binary search tree because it is a sorted tree. Okay, so that is the main difference between a binary tree and binary search tree. So that is the structure of a binary search tree. So we have seen what are binary search trees and we have seen the structure of a binary search tree. Now let's see what are the operations that we can do on this tree. So let's take a parent node. The first operation, let's say, is insert. Let's talk about insert first. So let's say there are no elements in the tree. So the first element is a root node. So let's say I'm inserting 100. So no problem. Now let's say I want to insert the node 90, right? So what would I do is, if it is a parent node, I will check whether the given node, which is the value 90, the value, is it less than 100 or greater than 100? In our case, it is less than 100. So we will go to the left of the tree and insert 90 there. Similarly, if I want to insert 110, we need to check whether 110 is less than 100 or greater than 100. 110 is less than 100, so we will insert greater than 100, so we will insert to the right of the tree, right? And let's say I want to insert the value 80. So what happens then? Let's say my insert value is 80. So for this, I will do level order search to find the position where I want to fit it. So first, I will go here. I find 100, which is the root node. Next, I will check, is 80 less than 100? Yes, then for sure 80 will be in the left subtree. I don't need to look at the right subtree, right? So I can traverse to the left subtree and then I go one level down. So in this level, I am checking, is 80 greater than 90 or less than 90? 80 is less than 90. So I will go to the left subtree of 90. So I will check here, is there a spot available? Yes. So I will insert 80 here. Right. Now let's see how to insert 95. So again, the same logic. We want to insert 95. So again, we will do level order check. First 100. Is 95 less than 100 or greater than 100? 95 is less than 100. So we will go to the left subtree. Now what is the left node? 90. Is the given value 95 greater than 90 or less than 90? It is greater than 90. So from 90's point of view, we have to go to the right subtree. So we are going to the right subtree. So is there any spot available? Yes, there is a spot available. So we can put 95 here. Okay. Now let's say I want to put the number 93. So where do I put it? Let's see. So again, first we go from top. Is 93 less than 100? Yes. So we go to the left subtree. Is 93 greater than 90? Yes. So we have to go to the right subtree. So is 93 greater than 95? No. So we have to go to the left subtree and we find a spot here. So we insert 93 here. Okay. So that is how inserts work. Right. So always we are trying to find the correct position based on the value. So that way our entire tree is sorted. Next, let's discuss search. So let's say I want to find the node 93. How do I find it? So again, applying the similar logic to insert. First, we will start at the root node. First, we will start here. So we will compare. Is 93 less than 100? Yes. Then we have to go to the left subtree. We know for sure that it won't be available in the right subtree. So from here, again, the same logic. Is 93 greater than 90? Yes. So we don't need to go to the left subtree. We will only find it in the right subtree. Again, going one level down. Is 95 greater than 93? Yes. So we will go to the left side of 95. So we will check here. So is 93 equal to 93? Yes. So we have found our node. So it is a binary search tree, which means it is a sorted tree. So we have to go one level at a time. We will either go left or we will either go right. Okay. So that is how search works. And now let's look at display. So display we have already seen in tree operations. So again, we can do in order search, level order search, we can do pre-order search and post-order search as well. So again, quick recap. So for pre-order, first the parent is printed, followed by left node, followed by right node. So if I want to print this one, 100, 90 and 110, first 100 is printed, then 90 is printed, then 110 is printed. For in order, first left is printed, then parent is printed, then right is printed. So 90, then parent 100, then right 110. For post order, first left is printed, then right is printed, then parent is printed. So 90, 110, followed by 100. For level order, we go one level at a time. First level is printed, which is 100. Then we go left to right in the second level. Then we print 90. Then we print 110. Okay, so this is level order. So these are the display operations that we can do. So we have seen search, we have seen insert, we have seen display. Now let's discuss remove. Remove is slightly tricky. So let's make a new tree so that we can discuss this. So I'll just make a tree again. So let's say this is our tree. For removal of a node, we need to take care of three different cases actually. First case is leaf node. So we are discussing removal cases. First is leaf node. If it is a leaf node, no problem, we can directly remove it. For example, if I want to remove 99, I can directly remove it, no problem. It does not alter the structure of the binary search tree in any way. We are still having the sorted tree structure, no problem. The second case is one child. It has only one child. If it has a child, then we will simply stick it to the parent, connect it with the parent. If it's one child, connect to parent. For example, let's say I have another node here called 105 and I want to remove 110, and 110 has one child, right? It is not a leaf node, but it has one child. So what do? I simply connect it to this guy. So the tree will become like this. And so on. So my binary structure is retained, right? So if it's one child, simply connect it to the parent, and then we can remove this. Right? Now there is a third case. It has two children. If it has two children, for example, I want to remove this node. I want to remove 90. It has two children, and children also have their own children. So what do? How do I retain the binary search tree structure even after removing 90? So think about it for a second. So somebody should take this place, right? Who can take this place? So there are two possibilities about who can take this place. So the first possibility is 85. This is the first case. And the second possibility is 92. This is the second case. I'll tell you why. Let's put 85 in its place and see how the tree looks like. So this is how the tree will look like if I put 85 here, which means see 100, 85, 85 is less than 100, fine. And whatever is in the left subtree is less than 85, whatever is in the right subtree is greater than 85. So we are still retaining the binary tree structure, which is good. Now let's see what happens if I put 92 there. Now this is the tree after removing 92, after putting 92 in its place. So we have put 92 and removed it from here. Now look at the tree structure. So 92 is here, which is less than 100, and whatever is in the left subtree is less than 92, whatever is in the right subtree is greater than 92. So this is still a valid binary search tree. If you put anything else, it will break the structure. So let's take an example. Let's say we are putting 80 here. Let's say we are promoting 80. So this will be the case if we are promoting 80 here. So I put 80 in the place of 90, and 80 has its own children, 75 and 85. So there is no place for 95 here. So we cannot put the third child. So this structure is broken, right? So what happens if you put 95? Again, same case. If I put 95 here, 95 will have its own children, and there is no place for 80. So again, the structure is broken, okay? So there are only two possible cases for deleting a node with two children. First is rightmost in left subtree, leftmost in right subtree. Only these are the two possible candidates who can replace it. And then after replacing, we can remove the child nodes. We can, even if 85 had something else, even if 85 had, let's say 82, right? Now 82 needs to be retained, right? So for that, we will follow this rule. This has one child, so connect it to parent. So we will simply connect 82 to 80, and we can still retain the binary tree structure, right? So if it is slightly confusing, just rewatch the video again. It will be a little clear. There are only two possible candidates for connecting, for removing a node that has two children. Okay, so rightmost node in the left subtree. So if we go down this tree, who is the rightmost node? This guy. This is the rightmost node in the left subtree, and this is the leftmost node in the right subtree, right? So only these two candidates can fit the bill. So if it is a little confusing, try to draw different trees and put see for yourself with different examples. Then it will be more clear. Okay. So that's how removal is done. We will code all this, so it will be more clear for you. So we have discussed removal. Okay. So in this video, let's keep it to theory. In the next video, we will try to code all this in C++, and then we will discuss the time complexities. Okay. So that is it for this video, guys. Thank you so much for watching. If you have any questions, definitely put it in the comments, and you can ask me via LinkedIn as well. Thank you so much for watching. And if you haven't subscribed to the channel, please subscribe and do share it with your friends. And do like the video if you found it helpful. And thank you so much for watching. I will see you in the next one. Cheers.